Okay, we are still talking about this baseband data transmission. So far what we looked at is this channel, the channel between the transmitter and receiver. This channel always has some multipath, and this one does not have ideal impulse response, right? When you look at the impulse response of the channel, you will see a multipath. So multipath means that this one is a single path. So you have this impulse response. That means this is ideal impulse response. But unfortunately, we are not going to get this impulse response. Instead, we are going to get multiple paths. Something like this, right? We have a many path. So this is what we call as a multipath. So we see this multipath in the impulse response. So because of this multipath, multiple path, we basically see that each multipath is working as a memory. Okay? So remember that multipath and memory and intersymbol interference and echo, all these are same thing. Right? All these are same thing. So because of these things, we have memory in the channel. So because of that memory, we have intersymbol interference. So that all comes together. So that's this channel. This is that channel. Right? So because of this channel, what we are trying to do is we cannot control anything about the channel. This is given to us. So that's why we are designing transmitter filter and receiver filter and put that all together so that from here to here, we are going to make an effective channel. And we want to make this effective channel to have impulse response like this. Okay? That's what we want. We want to make this effective channel to have this impulse response. Okay? That's our goal. Okay? Okay? Eventually, that's what we are trying to do. So our goal is, simply speaking, in order to make this red box to be Nyquist channel. That's what we are trying to do, right? So this is a Nyquist channel, and as you see here, Nyquist channel has this time impulse response and this frequency response. In the frequency response, your frequency will be limited into your bandwidth. You cannot use all the frequency, right? You're going to use only the given bandwidth. So when you have a rectangular frequency response, and take a IFFT, then you're going to see this sync function in time domain. Right? So this is the impulse response of Nyquist channel in continuous time. But what we are trying to do is, in this continuous time impulse response, we are going to do sampling. Right? We sample here, 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 so that when you sample it, it looks like exactly ideal impulse response in discrete time. So that's what we are trying to do, right? So that is Nyquist channel. So we want to make a Nyquist channel. So by doing that, by selecting the desampling frequency, you have sync function, but every zero crossing point, you have sampling. You sample it here, 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 every zero crossing point. Once you do that, now you only have a one tap. All the other tap has a zero. So that's why when you look at this one in equation, this term, right? The first term is this one. And all the other term, like these, corresponds to all the other zero samples, right? So that means this one, ISI term is gone, because you see that this one makes ISI, right? So all this term will be gone. Only this term remains, but this term corresponds to this, right? Do you see what we are saying? This one, right? Let me write this one again. This equation here basically means yi equals that multiply some constant, and xi, let's say x is the input. In this case, I is the input, but let me say x is the input. xi, so when you look at this, what is the relationship? This relationship is simply this, right? So this is a block diagram. This is simply equation. So you have x as an input, y is the output, but input output has the same index, time sample number I. So when you get ith sample in time, in input, at the same time you get the output sample. So no delay between these two, right? Do you see what I'm saying? If there is a delay, if you have this, right? If you have this, yi is a times xi minus 1, right? So that means we have a delay. Because we have a delay in the memory. This is simply a block diagram. This one is an equation. But that basically means that we have a delay because this time index is different, right? So we have a delay. But in this case, it's the same. So we have no delay, meaning no memory. So that's what we're seeing. This one here is same as this one, right? This one here is same as this one. So when you look at only this part, that means we have AI. That means your input and output has no delay, and simply a multiplying some coefficient, some constant value. Multiplying constant value doesn't matter because this one can be 1, right? So that basically means that as soon as you get input, you get the output at the same time. That's what we have here. What about the other terms? These other terms are something like this. Some constant, C, constant doesn't matter, so don't forget these things. Ci xi minus 1 plus some other C I minus 2 x I minus 2 something, right? And also some xi plus 1, xi plus 2. So that's all you have here. That's this term. And what is this term? These terms are all ISI. When you look at the impulse response of this system, okay, impulse response of this system, impulse response look like this, right? Okay, it's hard to explain here. This is impulse response. This is a block diagram. This is the equation. All three are same thing, right? These are the same thing. What about this? This is a block diagram. What is the impulse response of this block? This is impulse response of this block, right? Let's say we have this impulse response. What is the equation? Equation is something like the constant doesn't matter. Let's forget the constant. Make it this way. Something like this, okay? Something like this. So this is equation, this is impulse response. You can also make a block diagram, right? You can have two memory in this case. Okay? So always you want to get this relationship. This is what we want. Because if we have this impulse response, that means we have this equation and this block diagram between the input and output. And that's what we want. However, what is actually happening is, unfortunately, we have many other terms. So we need to remove this term. Because this term will create the ISI. Okay? So when you have more terms like this, right? This is actual channel. You have many paths. Because of these many paths, we have many memories. And because of all these things, your actual relationship is not simple as this. You have more terms, I minus 1, I minus 2, and x plus 1, I plus 1, I plus 2. You have infinite terms. Okay, infinite terms. All these terms corresponds to this one. And what we want to do is that, and all this term comes from this, right? Comes from this. Okay? Because we have this impulse response equation, we need to write it this way. So what we want to do is we want to remove all these terms. What we want to do is we want to remove all these terms. We want to remove all these things. So eventually we want to get this. Okay? That's what we want, right? So we need to remove that. That's the whole story. So final output that we want is Nyquist channel, because Nyquist channel is this. That is Nyquist channel. That's what we want. However, the problem of the Nyquist channel in the practical implementation is that when you look at the time impulse response, it has a negative time. So negative time cannot be implemented in practice. So this Nyquist channel unfortunately cannot be implemented in practical systems. That's why we need to design the pulse shaping filter. And this pulse shaping filter is trying to make as close to Nyquist channel as possible, but not exactly the same, but close. So this pulse shaping filter has two goals. The first goal says we want to we want to make the intersymbol interference to be 0. That basically means we want to have this. Okay? If you have this impulse response, that means no ISI. Okay? That's our first goal. Second goal is that we want to make the frequency response to look like this. This is the frequency response of the channel we want. Okay? That's the second goal. Let's go all the way. So this raised cosine pulse spectrum or pulse shape filter is one of the pulse shaping filter that we can implement. This one does not look like the same as Nyquist channel, but at least this one is pretty close. So how to do that is in time domain you are making this pulse shaping filter. Okay, in time domain. This is the case of alpha equal to 1 over 2. Okay? If we set the alpha equal to 1 over 2, we're going to get this. I'm sorry, this is frequency. We're going to get this frequency response. And once we have this frequency response, the time impulse response looks like this. Okay? That's the time impulse response in continuous time. In continuous time, right? Remember, this is just continuous time. If you sample at the right point, let's say you sample it here, you sample it here, 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 and here, here, here again, then you can also make this one as an ideal system, right? But look at the continuous time. This is a continuous time. It does not look like the same as a sinc function because sinc function it has a little bit little bit bigger side lobe. This is called the side lobe. Main lobe, side lobe. This one is a little bit bigger in actual sinc function. But our pulse-shaping filter is not exactly rectangular. It actually has a little bit slow roll-off here. So that's why you have a little bit smaller side lobe. Okay? But that's our impulse response of our filter. So we have a filter here. That's what we are talking about, raised cosine filter. This is a pulse shaping filter, but anyway, this is a filter. Pulse shaping filter. So of course, since this is a filter, you have an input and you have output. This filter has impulse response in time domain, and this is the impulse response of the filter. Okay? That is the impulse response of the filter. Now just guess what happened at the output. When you have this impulse response, let me draw the impulse response here. You have a small side lobe. You have a small side lobe and big. Let's say this is the impulse response of this filter. Now our input is rectangular input. What is going to be your output? Your output, like H, right? Think about you can do the convolution, okay? You can just calculate convolution using MATLAB or your computer. Just put this one in slide, okay? Slide. But between here, it's just 1, right? It is just constant value. So in between here, when you do the convolution, it's flat. Because once you put this one inside of this flat region, you're going to have flat anyway. But when this one is on the edge, left and right edge, then this value is going to be suddenly, it was a 0, but suddenly 1. So this one, when you put it from here, slide it to the right, then this shape will appear here. Like this, right? That's going to be your output. This is a very simple input that we use, but our input is not going to look like this, right? Our input is going to be like many data comes in sequential, right? You are not going to transmit only one value. We're going to transmit one after another, right? Many value, like a 0, 1, 1, 0, things like this, right? So for every rectangle here, you have this shape. So first rectangle, you have that output. Let's say for the second rectangle, again, you slide it, then you're going to get like this, right? Again, for the next one. Next one, again, you have these things. So these are all combined. Then eventually your output is going to be like something like this, eventually. So that's going to be your output. So compared to this shape, original shape, which is rectangle shape, eventually when you go through the raised cosine pulse shaping filter, your pulse will be shaped like smoothly, like round shaped, like this. So that's your output after the filter. Okay? But one thing that you can notice here is that we have a little bit of side lobe here, right? Small side lobe. If your impulse response is like this, right? In that case, your shape will be like this. But our impulse response has a side lobe. So because of that, your shape is going to be like this. And this one, you also have this. You have some ripple on the left and right. So this ripple, okay, what I'm saying is, let me put that again. So first one, you put it here in the filter, your output is going to be like this. Okay? So because of this ripple here, right? Side lobe, you have these things. Let me put the second one here. And then what you're going to do is you're going to get something like this, right? So what I'm saying is the ripple from the second sample and original first sample is combined. Same thing, first sample has a little bit of side lobe comes here. That one, the second sample will be added. So what is that? That is intersymbol interference. One symbol is interfering next symbol. That's the ISI. We have side lobe. So because of the side lobe, we have ISI. But you can remove ISI. How can you remove the ISI? By selecting right sampling. So if you select right sampling here, for example, right? Once you put the right sampling here, this is continuous time, right? You're going to sample it at some point. If you sample it right here, then this interference will go to 0. So you're going to get only the first sample because the second sample goes down to 0. Same thing here. Once you sample it here, for example, now then the first sample has no value here, right? So you're going to get only the second sample. So that's what I'm saying is a right point in sampling. If you sample it and at this point, let's say you sample it here. Once you sample it here, you're going to get the first sample, but you're going to get also the second sample a little bit. So that's all mixed. That's ISI. Okay? So that's all what I'm saying here as a pulse shaping. Okay? So let's move on to the next one. We also learned the eye diagram. So we have many words here, but let me move to the picture. So we have this receive signal. So this is a signal after the pulse shaping filter. So as we saw earlier, when you go through the pulse shaping filter, your output is going to be round because we shaped pulse. So this shape is the signal that you already go through the pulse shaping filter. So this one is the signal that we transmit, and this is also the signal we receive. Okay, we received this signal. Now once you receive this signal, and then we are gonna get the sample, every sample point. You look at this time duration, look at this time duration. So look at this one, look at this signal in the oscilloscope. Oscilloscope watches the signal in time domain. Right? So let's take a look at the oscilloscope. Then oscilloscope will show you this curve. But what we are trying to do is we are going to look at this area all together and put it in overlap. So the first region, we draw it here, then it'll look like this. On the same picture, we're going to overlap the second one here. So just copy that here. On the third one, again here. Like that, right? So we keep drawing here again. So that's what we are doing here in eye diagram. So once you do that, then we keep drawing each one of these in this picture. So overlap and overlap all of these samples, right? Then we keep doing it. Eventually, we are getting this kind of picture, and this picture looks like an eye. That's why we call that as eye diagram or eye pattern. And what we can see here is if the timing is very accurate, let's say sometimes the timing drift, and if there's no drift, then every time when you sample it at the right point, every time when you watch it at the right point, then you get this sample every time, the clear picture every time. But let's say this whole signal moves a little bit, the timing is off. If the timing is a little bit off, right, then when you draw this like 1,000 samples, 1,000 region, now then timing is a little bit off. So this one moves to the right, little bit, like this. Same here, moving a little bit off, right? That's what's happening. Here also, you're gonna timing, if you have a timing issue, the picture will look like this. So it's all dirty. So once you get this picture, now you get an idea. Oh, our signal or our system has a timing issue. You don't know how to correct it, but at least you can detect the problem. Oh, we have a timing issue. Okay? So that's one thing we can do. And also we have, let's say if we have a lot of noise or interference, then what is happening is that this one goes like this. If you have a lot of issue, then we have very small eye. If you have a lot of noise, let's see. If you have a lot of noise, what happened in the signal? Your signal, the signal that you are looking at here is very clean signal. Let's say you have noise. This is what you're gonna get, right? Let's draw it here. Then what do you get? The first one here, you're gonna get this. Second one, you're gonna get this. So if you draw that, then it's all like this, right? It's all dirty signal when you have a lot of noise. When you have a lot of interference, same thing. So by looking at this eye diagram, at least we can detect some problem. Oh, we have a lot of noise. We have a lot of the interference. Or we have a lot of timing issues. Something like this, right? So this eye diagram is used to detect that kind of problem. If the eye diagram looks like this, that means it's very, very clean signal. You have no timing issue. Noise is very small. So everything looks good in that case. So that's for detection purposes. Okay. What we are looking at today is channel equalization. Okay. In order to understand the channel equalization, we have to go back to the big picture. Okay. Let's go to the next slide and show you the big picture. So this is like a big picture. So far, what we discussed was, again, we have a channel between transmitter and receiver, but this channel is like this channel. We have a lot of memories and multipath and a lot of those things, right? So because of that, what we are doing is we are designing a transmit filter and receive filter, put that together so that here to here, we want to make it as a perfect channel or Nyquist channel. Okay, that was our purpose. However, the problem was that that's our dream. Okay, we want to design these two, put it together. We want to make Nyquist channel. That's our dream. In this case, dream cannot be true. So you cannot implement a Nyquist channel. So what we can do is we can design a pulse shaping filter. Okay, we design the pulse shaping filter and put it here. But the pulse shaping filter is not perfect. If the pulse shaping filter or our design is perfect, then what that means is here at this point, we should have no ISI. If everything is perfect, right? If everything is perfect, we are not going to have any ISI. And the impulse response of these will be like this. In that case, everything is perfect, right? but that is just a dream. So what is actually happening in the practical system is that even though we have these filters, things are not perfect. So some of the ISI will go over to the next stage. We cannot make it perfect, okay, in reality, in the practical systems. So we have some of the ISI remaining and go to the next stage. Okay, there's some interference remained. So therefore, what we need to do in the very next stage is, as a second stage of removing the ISI, that is why we need an equalizer. Okay? Simply speaking, this equalizer is a hardware block. And the reason we need this is to remove remaining interference, remaining ISI, intersymbol interference. That's the purpose of equalizer. Okay? Simply speaking, we need to remove ISI. That's why we need equalizer. Okay? Let's take a look at the name first. Why do we call this one as an equalizer? Maybe you can look at the audio, right? Audio system. Probably you heard about equalizer, right? In that case, why do you call that as an equalizer? Let's look at the equalizer here. When you look at the audio, right? Maybe you look like this, 500 hertz, maybe 1 kilohertz, 2 kilohertz, 10, something like this. And then you have a switch like this, right? So you can increase it, decrease it, something like this, right? You can do that. We call this one as an equalizer. Once you change this one, right? Change it up, down, up, something like this. What happened? Let's say you increase this. Then what are you trying to do? If you increase it, that means you are increasing the gain of this particular frequency. Let's look at from our engineering point of view. Since we look at the frequency and those things all the time, let me draw a frequency domain picture. This is a frequency domain. We have DC, 0. 500 hertz is somewhere here. 500. 1 kilohertz, 2, 10. Just example, right? Depending on your music or depending on your ear, maybe some people can hear 500 hertz better than others, right? Each people have a different ear, maybe some old people maybe has problem of listening some low frequency, right? So depending on the people, they have a different capability. And also depending on the music, some music has a very strong low frequency component. Some other music has some different frequency component. So let's say we have some music, and that music has this frequency response. Just example, right? Think about two scenarios. What I'm saying is, let's say this is a male voice, female voice. And there's one male, there's a female, they're talking same thing, same words, right? Same words. And let's take a look at, let's analyze the frequency of those two voice. Typically, male voice has a lower frequency, right? Female voice is a little bit higher frequency. These two people talking the same thing, same words, but each people has a different frequency, right? So we have a different frequency region. Same here. Every song, every music has a different frequency component. Let's say some of the rock music, let's say. I don't know, maybe rock music, some high frequency, maybe. some classic, maybe low frequency. I don't know. Something like that, right? Depending on the song, you have a different frequency component. So now let's say, as an example, for some one music, let's say we have this frequency component. For example, right? So this music, we have some pretty strong 10K frequency and pretty low 1K frequency, 1K hertz. In that case, what I want to do is that, I want to 10K frequency, 10K hertz frequency is too strong, so it bothers me, so I don't want to hear, I want to reduce this gain, okay, because this is too strong to me. And this one, I cannot hear it, so I want to increase the volume for this particular frequency, right? That's why you are increasing it, decreasing it. In that case, what happened is, you are decreasing it. So this is what happened originally, but I'm trying to decrease it because I decrease the gain, so you decrease it. 10K, 1K, I increase it. So what you're trying to do is I'm going to make it equal. That is why we call this one as an equalizer. Okay, that's what's happening. We call that as an equalizer. Equalizer. This is why we call that as an equalizer. So for the frequency domain point of view, the output of the equalizer is we want to make it equal frequency response. Okay, that's an equalizer. Then coming back to our picture, we are not talking about audio here, right? In this case, our system is not audio system. This is like a communication system. Then what's the relationship between this equalizer in audio system and equalizer in our system? Why do we have same name? What is the equalizer in our system? Actually, our system is exactly same equalizer as audio system. Because in audio system, again, it's a frequency domain. Okay, it's a frequency domain equalizer. Here, in our system, our equalizer is the same thing. We are trying to equalize in frequency domain. That's what we are trying to do in our system. So let's take a look at it. In our system, right? Let's say we are trying to equalize in frequency domain. If you have equal or flat frequency response, okay? If we have a flat frequency response, what is our time domain response? Time domain response is going to be this impulse response. And this is exactly what we are trying to make. Okay, this is our dream, still our dream. This one was our dream when we look at here, but unfortunately we cannot make our dream, okay, because Nike's channel was not implementable. So unfortunately we cannot make our this effective channel to be Nike's channel. Unfortunately, that we cannot implement it. This one was our just a dream. So that's why we have remaining ISI, but this equalizer will remove that remaining ISI. So from here to here, even after the equalizer, we are going to achieve our dream. This is our dream. This dream, same thing. That's why we are trying to make it equalizer. So using this equalizer, we are trying to make it equal in frequency, which is same as in audio system. Okay? So that is our goal. That's the concept of equalizer. Then how do you make it? How to make it is equalizer here actually is same as our filter. This is a filter. Okay, just regular filter. So let's take a look at filter then. When you take a look at filter, how do you make a filter? There are many ways to design filters. You heard about this one, right? What is this one? Finite impulse response. What is another one? IIR. Infinite impulse response, right? There are many ways. There are linear phase filter. There are constant phase filter. There are so many different filters. There are Butterworth, analog filter, digital filter. There are so many different filters, right? But typically, when you model the filter, there are so many different filters, but there is a common model for filter. How to model the filter is that the filter, every filter has number of taps. First, you need to decide how many taps you need. What is taps? Tap is like this. How many, in this case, this is tap. Each one is tap. So how many taps you need? That is what you need to decide. You need to decide this one. That's one thing that you need to do. Second important thing to decide is what the coefficient for each tap. So if you have like 5 taps, each tap has its own coefficient. So in that case, we have 5 coefficients. So this is all you need to decide. Every filter, you knew maybe FR filter, IIR filter, linear phase filter. Every filter, you need to design 2 things. These 2. Eventually, these 2. Okay, eventually. So come back to here. Actually, the name of this model is tap delay line model. Maybe in the DSP course, maybe you heard about this one. TDL, tap delay line. So what that means is every filter is modeled like tap. In this case, we have 3 taps. Tap, delay. Okay, every tap has a delay, right? This delay. Delay line model. So that's why we call this a tap delay line model. So based on this tap delay line model, what we need to decide is how many taps and what is the coefficient for each one. What is this value for each one? So that's all you need to decide for every filter. In FIR, since this is a finite impulse response, the number of taps is limited. Maybe 10 taps, 5 taps, because that's finite. But in IIR, the number of taps is infinite. Right? We have infinite number of taps. That's IIR. So that's why these 2 are different. So typically when we say filter, we generally say FIR filter. So this particular case, you see the delay line here. So that is, you see tap here. This is the tap delay line model. So this is a block diagram of the filter based on tap delay line model. So this is a filter. We have, in this case, we have a 2n-1, 2n plus 1 tap. This is the number of taps. We have 2n plus 1 taps. Each tap has coefficient. This is a coefficient, okay, for each tap. And this coefficient, each coefficient is typically a complex value. Okay? Each coefficient generally is complex, like A plus JB, something like this, right? It has its own amplitude and phase, typically. So in this case, we have a 2n plus 1 taps, and each tab is a coefficient, like complex value. So we have a 2n plus 1 complex values. That's all equalizer look like. Simply a filter. Then how do you decide the number of taps? That depends on the filter design, but number of taps is determined by many different factors. So in this case, we don't have to discuss those things. But typically, the number of taps is based on this, because what we are trying to do here is we have some remaining interference here, right? And equalizer is going to remove that. So how many interference goes over to the equalizer? How many interference? That will affect how many taps we need in the equalizer. If you have a more interference term goes to the equalizer, our equalizer filter need more taps. If you have only one simple interference goes to that, equalizer filter can be simple. Okay, so that depends on how much interference we have. So this one depends on how much interference we have. That was the first one. So this one is decided how much interference we have. Then how do you decide the coefficient? This one, right? Each one is a coefficient. That we need to calculate. We need to calculate each coefficient. So how do you calculate the coefficient of equalizer? That comes in the next slide. Okay? That's what we have in the next slide. What we are looking at in this slide, you see some of the equations, right? But forget the equation. Forget all this equation. Just look at this whole thing in a very simple block diagram. Let's say we think about the equalizer. Equalizer, again, is just filter. Equalizer. So since this is a filter, you're going to have input. Of course, you have output. And what output do you want? What does the input look like? Input is something like this. You have some signal. Input is like this. This is your input. Okay? You have some signal here, some symbol here, but the next symbol has interference in ISI here. So that is our input. So this input here is some received signal, but that received signal is not a clean signal. We receive some signal with ISI. Okay? So that is what is coming in. What is our output? Our output is going to be clean signal with no ISI. That's what we are trying to get, right? But anyway, this is filter, meaning that we have some impulse response. Every filter has an impulse response, right? So this one, for example, is an impulse response of this filter. Let's say our input is a C here. Our output is a P. And equalizer is a filter, so we have W, like a W1, W0, W1, something like this, right? That's what you have here. So when you look at this equation is simply a W convoluted with C. Okay, this is a convolution between W and C. C is the input. W is the impulse response of the equalizer. So of course we are doing convolution between these two, right? That's going to be your output. So your output is going to be convolution of W and C. This equation is same thing. We just make it as a simple. But same thing. Both are same thing, right? I is the sample index. I is the sample. K is the sample. I minus K. But when you look at the summation here, k is only from minus n to n. Why is that? Original definition of convolution, you need to have from minus infinite to infinite. But in this case, it's only from minus n to n. Why? The reason is our equalizer has 2n plus 1 taps. That's what we looked at in the previous slide, right? Look at the previous slide here. We assumed that we have only 2n plus 1 taps in the filter. So that's why if you have a minus infinite to infinite, that's okay. But eventually, all the other will be 0. Eventually, that will be simplified to minus n to n because we only have that number of taps. So we have this equation. But this simple equation is, again, convolution of W and C. Like this. That's the relationship. Now, let's take a look at the P. P is the output. What kind of output do you want? The output we want is this. This is the output we want. What is this output? This output will tell you this. If the I equal to 0, we have some value. If the I is not 0, if I equal to other value, all 0. So this is the perfect picture, right? This is our dream. Make it perfect impulse response. That's what we're going to achieve here at the output. So in this equation, this is the output, but we know that we want this output. So this is the output we want. So we can put this output, our dream output, here into P. In here, do you know the C? We know the C. Why? C is our input. We received already, right? This is our received signal. We already received some signal, so of course we know that, right? So we know this C. This one, this is our dream output. Only thing we don't know is W. W we don't know, right? Because what is W? Going back here. W is filter coefficients. That's W. This one. This is W. Filter coefficient. And what we are trying to do here is to calculate the W. Because we are doing filter design. We are doing equalizer design now. So we are trying to calculate the W. We know our output, dream output. We know the received signal. So based on these two, we can calculate the W. You can calculate, right? We know this one. We know this one. We can calculate the W in this equation. But this is like a summation equation. So it's a little bit difficult to get. So that's why in this summation kind of calculation, we're going to rewrite it into a matrix form. So this matrix form look at this matrix. This matrix form is exactly the same as the previous equation. This is actually the same thing. In the previous equation, it looks like Pi equals sigma k from minus to infinity to n wk ci minus k. Something like this, right? This equation, this matrix, same thing. You can try that, right? You can try that. This is our P. Let's say P, here, doing this calculation, C0, W minus N, plus, we have a C1 here, right? C1 times W minus N plus 1, dot, dot, dot. You have so many summation. That is going to be P1. Something like this, right? That is same as this one. Okay? So simply This is a summation equation. This is a matrix notation. Both are the same thing. So once you change this one into a matrix notation, now everything is pretty clear. We know this C matrix because C is our received symbol. So we know all these things. This P, we know that because we want to have this dream output. So we know this. Only thing we don't know is W. We want to calculate the W. We know this C matrix. We know this P matrix. We don't know the W. So how do you calculate the W? Simply calculating C inverse in left and right side. Right? Simply in this matrix notation, W can be simply calculated this way. Right? Just calculate the W, the C inverse matrix, and put it and multiply into P. Then you are going to simply calculate the W. That is how to calculate the equalizer filter coefficients, W matrix. Okay, that's all the story of W. That's all story. One thing that you can notice is that when you look at the C matrix here, this C matrix is a little bit special matrix. We call this one is a circulant matrix. Why is it circulant? That's because that when you look at the elements in the matrix, you see that C0 is here, here again, here again, here again, all these C0. C1 is here, again C1 here. It's like all the diagonal terms is same thing. Here is another diagonal, same thing, right? And not only that, let's say you have C1 here. Then C1, the last C1 appears here. It's like a rollover. We call this a circulant matrix. Okay? Let's say you have C2. Then next C2 should go here, but there's no column. So C2 will appear here in C2, something like this, right? So that's why we call this a circulant matrix. It's like a circular. Like these, and again going back and circular. So that's a circular matrix. So that's how to calculate the W matrix. And we call this kind of way of calculating equalizer matrix is a zero forcing. Zero forcing. Very common word. Every time when you hear about equalizer, you probably hear about zero forcing equalizer. And zero forcing, ZF, zero forcing basically means that you're going to calculate the inverse matrix and multiply it. That means zero forcing. Because when you calculate the inverse and multiply it, that means cancel out, right? You have, in this case, you have C, and you are calculating C inverse, so it's cancel out. So that's what they mean as a zero forcing. So this kind of equalizer called the zero forcing. Okay, so coming back to this picture. Let me show you in the picture what is happening once you do this. Let's say our original GF, CF, right? CF. Yeah, CF look like this. What that basically means is that from here to here, that's a CF. From here to here, if everything is perfect, then we are going to have a flat frequency response. And in time, only one impulse, if everything is perfect. But unfortunately, here in the CF, it's not perfect. So that's why we have a multiple path still remaining, some of the ISI still remaining in time domain. But in frequency domain, it's not flat. You have some fluctuation in frequency domain. So that's what you have here. So that's here, right? This is the frequency response of the signal. Now what you're trying to do is that you are calculating the inverse equalizer. This guy is putting the inverse of that. Look at the blue one and red one. Red one is actually inverse of that. Inverse of blue. Okay, once you inverse of the blue and multiply these together, then what happened? It's like a cancel out and becomes flat. So eventually your output here, output of the equalizer is going to be flat. Eventually. That's what you're trying to do. Then why do you multiply it? Let's come back here. In time domain, your input time domain signal and your time domain impulse response, we are doing convolution of these two. Then you're going to get the time domain output. Time domain, right? Let's look at the same thing from the frequency domain. You have this frequency domain response here. The frequency domain response of your equalizer is going to be inverse of that. Time domain convolution, frequency domain multiplication, right? So you are doing multiplication of these two. Like a multiplication of blue and red, you're going to get flat. That's the idea. So eventually, when you multiply, so that's how we design the equalizer. This equalizer has inverse frequency response of the input. So that you want to cancel this out. Then eventually your output, you have equal frequency response at the output. So H equal, this equalizer frequency response will equalize frequency response. That's the purpose of equalizer. Okay? Okay, so let's continue next time.